Good evening, this is Amos Tarfa with LifeSTEM Academy, just making a quick video about the most beautiful equation in mathematics, the Euler identity equation, which is e to the I pi plus 1 is equal to 0. So you might have seen this somewhere, which of course means that e to the I pi is equal to negative 1. So one of the proofs that we can use is using the power series. I'm going to establish some fundamentals which you can go back and review later. But we have cosine x and sine x. We have these written in a certain series here. And we're going to use this later on. But just keep in mind that the things on the right side are established principles that we can discuss later. So cosine x is 1 minus x squared divided by 2 factorial. And remember, factorial is basically when you take a number and you multiply from that number down to 1, right? So 4 times 3 times 2 times 1, that would be 4 factorial. And then you multiply these together, you get 24. So 4 factorial is 24. That's what the factorials are in each of these problems. Now notice a pattern with the cosine factorial. It's even, right? We have even numbers there. And then with the sine x, we have odd numbers. The other thing that is interesting is with complex numbers, when we talk about imaginary numbers, I to the 0 is 1, I to the first power is I squared is negative 1, I to the third is negative I, and I to the fourth is 1. Those are the, that series repeats. So if I ask you what is I to the 8th power, you would actually say the answer is also 1, because I to the 8th power is just I to the 4th times I to the 4th, right? So those are some of the things we need to show this proof. But we're going to come over here now and say, for example, if you have a complex variable z, the power series expansion of e to the power z, right? So e to the power z would be 1 plus z divided by 1 factorial. So technically you could say z to the first power divided by 1 factorial plus z squared over 2 factorial plus z cubed over 3 factorial, and notice the pattern, and so on and so forth. So if we start with this premise right here, right, we have this power expansion going on, and then if I said, what if we substituted, instead of z here, what if I said let z equal I to the x? Let z equal I times x, sorry, okay? So then, instead of e to the z, I'm going to say e to the ix. Well, what does that mean? That means that everywhere you see z, you're going to replace it with ix. So we have 1 plus ix, right, to the first power, divided by 1 factorial, plus ix squared divided by 2 factorial, plus ix3 divided by 3 factorial, plus ix to the 4th divided by 4 factorial. Okay? Now, let's try to simplify what this looks like. E to the ix is equal to 1 plus ix over 1 plus I squared x squared over 2, right? What is I squared though? That's negative 1. So remember, that's why this was important. Plus I cubed x cubed over 3 factorial. But here's what's interesting here. When you have a power outside of parentheses, you're allowed to distribute in. That's from the rules of exponents. Okay, so that's what you get there. And then here we have I to the 4th, x to the 4th, or 4 factorial. So let's examine. We're going to notice a pattern here. First of all, this will just come down as 1 plus, this part here just becomes I times x. This part becomes negative, because that is a negative 1. I squared is negative 1. And this becomes, so think of it as negative 1 times x squared over 2 factorial. This part just stays, I remember I to the third is negative I. So that becomes negative I times x cubed with 3 factorial. This part becomes 1, right? So x to the fourth over 4 factorial plus, okay, there's going to be a pattern here. But notice that some of these have i's and some of them don't. So let's split them off, the ones that have i's and the ones that don't have i's. So we have 1. So the e to the ix is equal to, we have 1 by itself here coming down, ix. Why don't we put the one with the i's over to the right side? And let's bring this one over. Minus x squared over 2 factorial. And then let's bring this one over. Plus x to the fourth over 4 factorial. Okay? And this is going to continue. There is going to be a pattern. And then for the ones with i's, we're going to have plus ix, right? Minus ix cubed over 3 factorial, right? But then imagine if I took out all the values of, if I took out an I and wrote down what was left inside the parentheses on this side. That will then become we have the left side, which is e to the ix is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial plus I into x minus x cubed over 3 factorial plus x to the fifth over 5 factorial and that's what's going to happen. It's going to form a pattern of x minus x to the third power divided by 3 factorial plus x to the fifth power divided by 5 factorial. But what are you noticing? This looks very similar to something that was discussed earlier. That looks to meet up with that pattern that you did with cosine x earlier. So e to the ix is equal to, this pattern is actually cosine x. It follows the pattern of cosine x. This over here follows the pattern of sine x. So this follows the pattern down here, of sine x. So that's sine x. So this one follows the pattern of sine x. So now notice that cosine x is the same as this. Sine x is the same as that. And now we have e to the ix is equal to cosine x plus I sine x. But remember, the most beautiful equation in mathematics is e to the I pi is equal to -1, or e to the I pi plus 1 is equal to 0. So now what's going to happen? We have to let x equal pi. So e to the I pi is equal to cosine pi plus I sine pi. Well, cosine pi is equal to -1. Sine pi is equal to 0. So now let's substitute that back in. E to the I pi is equal to -1 plus I times 0. Anything times 0 is 0. So e to the I pi is equal to -1. Or e to the I pi plus 1 is equal to 0. That's the proof for Euler identity, the most beautiful equation in mathematics. Thank you for watching this video, and I'll be putting out more videos on the history of math, applications of math, just math problems for our students. You're welcome to check them out. And if you have any questions about Lifestem Academy, let me know. Have a blessed day.